Hello?
Hello?
Yeah, but
Hello? Hello,
yeah,
Chandra?
good. Yeah, I can hear you.
Yeah.
Great.
Better, right?
Okay, great.
Good. That was better. Yeah.
Yeah. Great. So I think Satria will start. Satria.
Yeah, allow me to start, sir, because it's already 8:27 and we will start the session at 8:30. So let me do the opening sentence and allow me to introduce Professor Ngo as well. Okay, I'm going to share my screen. Excuse me. Okay, first of all, good morning, ladies and gentlemen. Before we start the presentations, and in order to avoid any disturbances during the presentations later, I would like to ask everyone here to mute their Zoom. The honorable speakers, distinguished guests, fellow audiences, ladies and gentlemen, good morning to all of the participants in the training course, and also my warmest greetings to the audiences that are watching from our YouTube channel. My name is Satria, and I am pleased to tell you that I will be act as this morning session's moderator. First of all, I would like to welcome you all to this webinar about technical aspect on wastewater treatment held by Center of Environmental Studies, Bandung Institute of Technology. In this occasion, we shall have an outstanding presentation from our prominent presenters, Professor Ngo, who is already here at the room, whom I believe shall enrich our insights and knowledge regarding the theme of this seminar, especially on membrane bioreactor on wastewater treatment. Before the presentations begin, allow me to introduce the presenter. Our presenter today is Professor Hu Ngo, and he is a professor of environmental engineering from UTS, or University of Technology, Sydney, Australia. Professor Ngo is currently a professor in environmental engineering and serving as a deputy director of Center of Technology in Water and Wastewater, co-director of Joint Research Center for Protective Infrastructure Technology and Environmental Green Bioprocess, School of Civil and Environmental Engineering, Faculty of Engineering and Information Technology, University of Technology, Sydney. Professor Ngo is internationally well known for his activities in the areas of advanced biological wastewater technologies and membrane technologies, and he has published more than 500 technical papers, including more than 350 SCI journal papers, over 100 conference papers, 4 books and 28 book chapters, and a number of patents, while receiving several highly recognized honors and awards. So without further ado, because Professor Ngo is already here, I would like to welcome our presenter, and Professor Ngo will deliver a presentation entitled Anaerobic Membrane Bioreactor for Future Sustainable Wastewater Treatment. For those of you audiences from whether in the Zoom meeting room or the audience in the live YouTube, you can ask questions by typing in the live chat column or by typing in the Zoom chat feature. So ladies and gentlemen, please welcome Professor Hu Ngo. And Professor Hu Ngo, the session is yours. Thank you.
Okay, please.
Good morning, everyone.
Good morning.
Thank you very much for very nice introduction. And so that's why I'm not going to talk about myself for further, like the information. But anyway, firstly, I would like to thank you so much, Professor Chandra Setiadi. Is my good and old friend. And that is such. And this is the first time for me to attend your research center webinar. That is that. Yeah. This is the first time, and I'm very happy about it.
Thank you.
Okay. So today, I would like to discuss with you all regarding anaerobic membrane bioreactors for future sustainable wastewater treatment. In fact, is that, I mean, like the recent days, anaerobic MBR, I mean, it seemed to be very, very hot topic. And it seemed to, I think about 10 years ago, at that time, I tried to convince the people, so good, anaerobic MBR, but I mean, the people is not really, I mean, recognize this kind of technologies. But currently completely different. Thousands and thousands of the researchers that, I mean, like that work on that, the anaerobic membrane bioreactors. So this is the way, I mean, today I try to say about that and just let you know is that technology will be a future sustainable wastewater treatment. Okay, so the content, whatever I want to talk today is quite a lot. So firstly, just go through the background first. Okay, so you can see it's a third generation when we want to treat the wastewater. You can see very lengthy process from the pre-treatment, come to the primary, and then we go to the I mean, like the biological treatment process, and go to the secondary clarifier, and then we go further for chemical sedimentation, and then sand filter and disinfection. Then we can discharge our wastewater to the receiving water bodies. And then it's too long, so that we think about the second generation. So in the second generation, we shortcut here. That means that after the second clarifier, we go for the sand filter and then disinfection and just discharge the wastewater, but still not good. So we go to another generation, we say a third generation, and then that is a really, really short. And it seems to be, we only need the pre-treatment and then MBR, membrane bioreactors. And this is the Biogas membrane bioreactor is that about, I think it's that 17 years ago that already reached the third generation. Okay, so now we just see the conventional wastewater treatment, why they have some disadvantages. And we need to use some, I mean, alternative technology or something like that to support for the conventional wastewater treatment. Firstly, think about it. When we talk about the conventional wastewater treatment, until now, no way we can use conventional wastewater treatment for decentralized system. No way. We cannot use for even one building or even one apartment or whatever, or school or something like that, or hospital. No way. So that is that we send centralized feature and then mixing with various wastewater. Because in somehow from the wastewater treatment plant, we may, I mean, combine with some industrial or something like that together. So that is the way, because it's quite far and quite long, and the pipeline is a very, very long. And then substantial chemical use. I show you the process. Think about it. Whatever, how much chemical we add into this process to make that I mean, like the to reach the discharge standard, I mean, effluent. So this is another disadvantages. And then the massive residual, the sludge production is unbelievable. And then we spend a lot of money just because of that to treat the sludge. Because the wastewater, as you know, is that we treat the wastewater only 50% of the cost, and the sludge we need to spend another 50% to treat the sludge, but sometimes it's more than that. In fact, maybe 60%, but wastewater only 40%. Now we come to the value of recovery resource. Resource recovery these days is really important because we aim for the zero waste, and also we want to convert waste to become the valuable resources. And then the conventional wastewater can't do this This is that. This can't. They just only, the function just only remove the pollutant, and discharge the wastewater. That is unfortunately. And then inflexibility. Why we say inflexibility? Because it's long process, and also we cannot just, for example, 500 people, 5,000 people, 50,000 people, 500,000 people. It's not flexible when we design like that, because the bioreactor, especially for the HRT, the hydraulic retention time, the volume, and then in different ways that we can't be not very flexible in, design the system. And then massive footprint, I mentioned to you, is that of course it needs a lot of, like the big volume units, and then it's the big space to have the conventional wastewater treatment. And then energy intensive. Just because when we talk about that, is that almost is that the pump during the process, and that is especially air diffuser. It costs a lot of money because it's, the energy consumption is very, very high. So then the conclusion is go to what? First, money. Second, energy. And then experts. And then is that value land. That it will in fact, will have impacts on this kind of thing, 1, 2, 3, 4. And that is really the matter. It's really the matter. Okay, so now the people before, about 15 years ago, 20 years ago, the people just only think about Anaerobic MBR, because very popular even until now. Quite, a lot of countries still, like apply the Anaerobic MBRs. And we'll see the Anaerobic MBR first, all right? Anaerobic bioreactor, for example, activated sludge, or trickling filter, or like the US, for the this is the Anaerobic MBR. And then we add the membrane either inside the Anaerobic bioreactor or outside the Anaerobic bioreactor. And then the definition is MBR. The MBR is, in fact, is quite simple. But when the people think about Anaerobic and Anaerobic MBR, they think about the membrane can do the, bio function. No, not at all. The membrane only do the physical filtration. Not more than that, not more than that. Okay, so this is the definition of the Anaerobic MBR. Now we come to that. What is the, the merits of the Anaerobic MBR? It's a good thing just like that. You see, this is a basic thing. Why we use the membrane for? The membrane is that stop first because filtration. So they separate, the solids, okay? And then we will have a clean water. But at the same time, the membrane can, retain the microorganism for us to do the job. They are cleaner. So if we wash out on the, the microorganism, then we do not have any cleaner to treat the wastewater for us. So that is the thing. And here you can see solids and microorganism retain separate. You can see this is the point. All right. So now come to what? Come to the advantages of that. First of all, excellent microbial separation ability, because they can retain the microorganism. Second thing is that control it's easy to control the hydraulic retention time or sludge retention time. And just because of that, very flexible. We can design only for 5 people or 50 people or even 10,000 people, still okay. We can use the MBR, all right? But it's a very good thing is that smaller footprint. Because for the MBR, even if it's 10,000 or 10 whatever, the HRT is only 3 to 6 hours to 8 hours. It's not like the other bioreactor go to 12 days, for example, or even a month. This is just because of that, it's really big, big footprint, right? But for MBR, very small footprint. And then low rate sludge production. This is the, the good news for the people who like to use that the MBR, because the sludge production is very less. And then we can save the money from the sludge treatment. And then high biomass content. So that means about 10 to 20 grams per liter. We need that, the quantity of the microorganism to do the job. But the good thing, because if for the activated sludge, for example, they may use only 5 grams per liter. And if more than that, they have to, they have to control the HRT, and also they have to replace the sludge and a lot of things there. So it's not good. So this high biomass is really, really, crucial, for the MBR. And then flexible is all right. And then the last one you can see is high quality. Because after the aerobic MBR, whatever they discharge, the quality is quite high. Okay, the quality is very high. All right, so now, however, why I put however? Because, yeah, so aerobic MBR is very good, very good, very good. But that's the very important is that aeration. Because we need the air pump, we need the air diffuser to provide the air into the system continuously. We cannot stop. So that's why the energy consumption is very high. And that's why is that we have to think about it. And when we want to think about it, then we have to think about an aerobic MBR. And that is, I just said about the energy consumption. But the other one is even much more important. That is, we can produce the bioenergy. But the aerobic MBR cannot produce biogas. An aerobic MBR 100% can produce biogas, right? So this is just something we have to think about an aerobic MBR. And then we have to make it for, to become very popular. As the aerobic MBR we use at the moment. Okay, so now we just see, we just see the whole thing is that about the evolution of the anaerobic MBR. When we do like that, is that we only start from the 1978 for the first anaerobic MBR. Okay, and then Professor Hans is a very, the very famous person at that time who invented, the anaerobic MBR in that only lab scale. But come to the 1984, the anaerobic MBR become the first commercial, the first commercial anaerobic MBR. Whenever they treat is that almost like the more in the industry waste rather than, the domestic wastewater. And then in 1987, we have the anaerobic digestion ultrafiltration. And then they try in the pilot scale and full scale plants or something like that. And very good as well, because successful in the full scale. And the full scale is that, as you say, a lot of technology, they only reach to the, pilot scale and then finished. For example, MFC. It's nothing there in, for the full scale, for example, I just say. So is that successful? In 1987, already successful. And then 2009, we have a very nice cupola, submerged and aerobic MBR, full scale in food and beverage industry. Very successful at the full scale. Again, that full scale. And then 2010, The largest one is that anaerobic MBR food wastewater treatment. So that is the story about that. Of course, it's quite a few lab scale. You know, we work in the lab or something is quite, I mean, like successful, quite successful. And then one of thing is that, for example, I just say here, because the slide, I mean, like the animation have some problem. So that's the reason I can't show you step by step. But anyway, just one here, you can show is that the performance for, I mean, like the anaerobic MBR to treat that the canned food, I mean, like the food wastewater, and the COD removal up to 99.4%, suspended solid removal 100%, and then methane, that is the biogas production, up to 8,500 cubic meter per day. You can see it's quite good. In fact, is that when we look, it's very, I mean, like very attractive. But in fact, it's not like that. It's not like that. So that's the reasons quite a lot of countries, they still don't like to use an anaerobic MBR. We have some, I mean, like the disadvantage, and I will talk to you later on. Okay. So after the background, after we understand, then we go to an anaerobic configuration. And what is that? You just see, very easy. We have an anaerobic bioreactor. What means anaerobic? Of course, everyone should know about that. Aerobic with the oxygen, and anaerobic completely without oxygen. Okay. And then if we put the membrane outside the, I mean, the bioreactor, that is the external growth flow and anaerobic MBR. But if we put the membrane inside the anaerobic MBR, an anaerobic bioreactor, then we can have a submerged anaerobic MBR. And then you can see and then we can divide in two groups. The first group is that we put the membrane inside the bioreactor. The second group is that we put the membrane inside a separated bioreactor. It's very interesting. And then you will see. This one is external growth flow and anaerobic MBR. You can see we have a growth flow membrane module here. And then we can have an anaerobic bioreactor here. And then they produce the biogas. You can see the biogas. And then this influent coming. And then effluent come out, but the sludge. So that means we have to recirculate back to the anaerobic MBR. All right. And here we can have a sludge retention time controller. So it depends on, I mean, the sludge, you just say about 3 months, 6 months, I mean, 1 year or whatever. But of course, we want to have as long as possible, the sludge retention time. So just because of that, we just, I mean, like, just say something about the external growth flow and anaerobic MBR. The advantage, high flush, yes. Easy clean and replacement, because they put it separately. The membrane in all the units, so very easy for cleaning and replacing or replacing something like that. But unfortunately, because they use it, the feeding and go through the cross-flow membrane and recirculate back to the anaerobic MBR, so the energy consumption is high. And then is that we need to clean very often also because of that. And the last one is disruption of biomass activity. The people say, yeah, what you mean disruption of biomass activity? Because you see, if we only one here and you put the membrane inside, when we retain the microorganism in that bioreactor, so they keep doing the work. They need not to go through the other module and then recirculate back. So that the reason is, I mean, like disruption. And then, I mean, like of course, bacteria, they are not happy, because it's one day they keep moving again and again and again, something like that, right? So this is the disadvantages. Now we go to the submerged anaerobic MBR. Very simple. We only put the membrane inside, I mean, like the anaerobic bioreactor. Yes, we have a biogas here, and then effluent come in, and then effluent. This one is vacuum suction pump. The other one is feeding pump, just force from feeding. This one is suction pump, okay, vacuum pump. All right, and then similarly, we have HRT controller. That's a sludge retention pump here, and then just simple like that. This is very simple, but the advantage and the disadvantage we can see. Yes, the energy is lower because you one unit, and very simple. We can design easily, and operation condition because it's that whatever in one unit. So condition is quite okay. Disadvantages, we are not really happy about the removal efficiency. Even, I mean, like the organic removal efficiency, like COD, BOD, and the nutrient removal efficiency is quite bad. So that means quite low. Okay. So what the people think? Okay, just like because of that, why don't we do another idea? That means two-stage submerged anaerobic MBR. So that means they have one anaerobic bioreactor here, and then another one. So that means we have two, but we put in the second one. We put the membrane inside the external bioreactor. So that means that this is the concept. They send back they recirculate the sludge back to the first anaerobic bioreactor to support for the biological, I mean, like the process. All right. So this one, of course, when we see like that, we are very happy because of what? Higher removal efficiency and gas production. Because double, think about it's a double. So that means gas here, and gas here, and also even whatever we have the better, I mean much better the efficiency. But disadvantages, yes, we have to pay for that. You just remember is that whatever we pay, whatever we get, that is the point. This is a principle. So we can't, I mean, like when we want to have the better removal efficiency and the gas production, we have to pay for that. All right. So after, I mean, I just introduced about the anaerobic MBR configuration. So now we just have a little bit idea about the pollutant removal from an anaerobic MBR. Lab scale. You can just see the lab scale, whatever, different types of the wastewater. You can see from the palm oil mill, or I mean like the slap the house or leaches or whatever. And then they control in different organic loading rate, hydraulic retention time, sludge retention time, I mean like and then the total suspended solid. So that means the biomass from the beginning, they put, the total suspended solid that for that kind, for this kind of treatment technologies. And then what we just see from here, the COD removal is not too bad, especially for palm oil mill from 96 to 99. And for example, the pre-worry with sublet yeast more than 97. And then the crop evaporator condenser or something 97. So most of, I mean like a few, only the few is very, I mean, vary a lot. For example, slap the house, it's not really good because it's that the rent is too big. Like this also, the second one, the thermomechanical popping press stage also is not so good or something. So that in the lab scale, we can see the weakness of the anaerobic MBR. It's not really, I mean, like perfect in the way like we use the anaerobic MBR systems. All right. And then we go to the municipal wastewater now. For municipal wastewater, they use in different, I mean, like configuration. They have summer MBR, external MBR, or the anaerobic MBR, external one, and separate one. So when you see like that, you can see about the removal efficiency in somehow is not really, I mean, like the impressive. Just only that suspended solids is quite impressive, but this one's 88%, and this one is about, I think is about 46%, and for the external one is that you can see the COD only 87%, 73%, or something like that. And this one is 88%. So it's not really impressive. That's the reason why the people is a little bit late to apply this, I mean, like the technology. Okay, so now the summary. We can say high removal rate of COD and TSS, but I just say TSS is yes, really high, but COD very, I mean, like the uncertain. So that means that sometimes very high, sometimes very low, and during the day up and down quite a lot. It's not stable, okay? And the moderate removal rates of endocrine active compounds and pharmaceutical active compound or something like that is not bad when we use anaerobic to remove that, and even anaerobic, the antibiotic. We work on that and we know it's pretty good as well. But the very sadly say low total nitrogen and total phosphorus removal rate, low, very low. So that's why it's very disappointed about this system, about the nutrient removal. Okay, so now we go from the lab scale. We go further. We will see about the pilot and the full scale. What is the pilot and the full scale then? Because only the pilot and full scale, we can see whether it's applicable or not, whether we can really go ahead with that, but not the lab scale, All right. And then what we just see here for the different kind of the wastewater. Okay. We say, for example, ethanol thing, stillage, snack factory wastewater, potassium processing or food processing, etc. And then it's the good news when we go to pilot and the full scale, we just see the COD removal here, 98, 97, 95, 99, 99.4. So that is the really, really good news. But when we say the good news, we need to be very careful. I mean, what we say very careful about the, I mean, like the flush, because the flush is very low, only 4.3 liter per square meter hour, very low. This one is okay. This one is, I mean, 8 up to 8 is all right, but this one very low, and this one extremely low, 0.83 to 5. I mean, that's very low. This one also very low. So even though we have a high, I mean, like the COD removal efficiency, but we still need to consider. All right. So that is the thing. Now we come up with the real application of an anaerobic MBR in the world. And I selected, I mean, about 3 case studies and let you know is that the first one is an anaerobic submerged hollow fiber MBR pilot scale in Spain. And that is the thing is that I just want you to have a look at that. This is that they are running, and the COD removal up to 97%, roughly that. And the biogas methane, I mean like 0.069 liter per gram COD, very low. That is not good at all. The theoretical, I mean like the, The theoretical methane yield is 0.294, and this one's only 0.096. Sorry, on 0.069. It's too far away from the theoretical, value. So that is not a successful, like the case study. Now, we go to the case study 2, Kubota process. This one is completely different story. This one is really, really successful about the anaerobic MBR. What they said is that they have the, like solubilizations, and then they have a thermophilic and mesophilic digester, okay, whatever they have. But the only thing we don't care, whatever, they just want to have that biogas linked with the submerged membrane reactor, reactor. All right, and then they can discharge, and then they have a okay to they satisfy or they meet the discharge standard. So that is the good point here. But another good point is that they produce a lot. The system, the anaerobic MBR produces a very high biogas for power generating facility, boiler, and so on. So that system is that they don't need to use the normal like coal-based electricity or something like that. They rely on their own, like the anaerobic MBR system to support the electricity. So that is really sustainable, really sustainable. And the wastewater is the shochu, that kind of the alcohol. Japanese and Korean, they love very much shochu. When we talk about shochu, we know that about that. And because of the very successful, so Kubota, they already in Japan until 2010, they have already have 15 full-scale plants. All right. So this is that one successful. And then about the membrane, okay, about the membrane, they can retain the methanogenic material that the bacteria produce biomethane, okay, and then they can filter out dissolved methane inhibitor such as ammonia. So that means they're very good in the biogas production. In somehow, because they have two good points. And then the digester. Basically, normally the digester, for example, 1 cubic meter. But for this one, become only, 0.3 cubic meter. Or, 0.2 cubic meter or something like that. Because the volume is about, about 1/3 to 1/5 times of the traditional digester. And the biomass 3 to 5 times of the traditional digester. That is really the good news, because the more number of the biomass, the better. Because they eat more. We just say eat. They eat more. They break down more organic matter. So that's the reason they can remove, they can convert the organic matter to become biogas, and at the same time, they can remove almost the organic matter in the wastewater. So that is the pretty good. Okay, so now another happy case study, whichever I like to show you. That is it seems to be very new one. This is just only 5 years ago, very new, brand new. Like something like that. And then what you just say here, this is the distillery waste treatment by Veolia, UK, in Scotland. And then the distillery, whatever, they have the pot out, they have a wastewater, they have a spent lease, whatever, the wastewater to come with the total flow rate is 400 cubic meter per day. And then is at about 12 tons COD per day. So when they come to that anaerobic MBR here, they produce 5,500 cubic meter per day biogas. When we talk about biogas, so that means definitely the major one is the methane, and then nitrogen, for example, or the hydrogen sulfur. I mean, like that kind of, I mean, like gas. Okay, but major one is the methane. And then is that this kind of biogas can support, can generate 1,600 kilowatt per day. All right, so that is really, really nice. I mean, every day they from this quest to convert to that 1,600 kilowatt per day. And at the same time, they can treat very nicely. I mean, like can treat very nicely the wastewater to discharge to the water course without any problem. So that means they don't react. They don't cause the pollution, water pollution problem. But at the same time, they can produce such a good, I mean, like the bioenergy. Okay, so now we come to the biogas production. When we talk about biogas production, we just think about it, waste minimization, because that's why we have to think that way. Because the convert from, for example, the per gram COD removed, and this one is the sludge production. Okay. So this one for anaerobic MBR only 0.031, and this one is 0.420 gram, too far away. So that means anaerobic MBR produce sludge much more than anaerobic MBR. So that is why we like anaerobic MBR. Because anaerobic MBR to become, I think, kind of the green and sustainable, just because of that. Short HRT for anaerobic MBR, long HRT for anaerobic MBR, then we can have a low sludge yield, and then we can spend less money for sludge handling and disposal costs. This is the biogas production. Actually, you can see from this, I mean, like figures, it's very easy to understand that we have in the wastewater, normally it's complex organic matter is there. And then we need in the wastewater, the busway, the conversion busway, we go to the first stage, okay? That means hydrolysis. And then the complex organic matter to become soluble organic molecule. And then the second stage to convert to volatile fatty acids. And then the volatile fatty acid will convert to the hydrogen carbon dioxide or acetic acid. And this is very sensitive. This state is really, really sensitive, because if we don't want to go further, we have a clean, if we don't have, we have a clean biohydrogen. And then if we go further, then we have a methane, but methane is not clean. Because through the, the combustion or something, they become the green gas emission, okay, greenhouse gas emission. All right, so this kind of thing. So when we come to the biogas production, you can see so good. Biogas conversion efficiency up to 98%, methane yields at up to 0.33 liter methane per gram COD removal, and methane up volume per volume biogas normally 90%. So that means methane is the main one, and the energy generation rate is about 2.02 kilowatt hour per kilogram BOD removed. All right. So this one is pretty fast. We just see is that about the methane, production, 0.31 to 0.34 cubic meter per kilogram COD removed. So that means 1 kilogram COD removed, we will have that 0.31 to 0.34 cubic meter. The only thing we need to think about it, when we work on the methane have a headache is the dissolved methane. Because why we cannot collect 100% methane from the treatment from the anaerobic MBR? Because that's almost about 50% or 40% or whatever, they dissolve in the wastewater. So when we discharge the wastewater out, CA4 will go to the air and create the global warming problem. So that in the future, I suggest the researcher think about it, how to reduce the dissolved methane, and increase that the methane, like the collection quantity. All right, this is a very interesting research. Okay, and the operating parameter for biogas production, and you know that is the four main operating parameters. One is temperature. Okay, temperature is, we have a cycle prophylact like the 10 about, like about 10 to 15 centigrade or something. Mesophilic about, I think, 25 to 35, roughly like that. Thermophilic about 45 to 85 or something like that. But whatever, why we have different kind of temperature? Because the temperature different, the removal efficiency will be different. The MBR reactor size is different as well. Very, that significant impact because of the temperature. The pH is the range about 5.5 to 8.2, so that's all right. The HRT, lower HRT, we will have the smaller reactor, of course, because HRT is that equal V divided by Q. So the volume, the HRT is higher, the volume, of course, is bigger. The slot retention time, HRT, is the longer one. So we will have a lower sludge yield. But the only thing is that the longer one, they will have that kind of age. And maybe the removal efficiency will not the same. So that means that lower removal efficiency, pollutant removal efficiency. All right. The inhibitors to biogas production. Yes, we have problem. If the ammonia higher than 3,500 milligram per liter, they become the inhibitor for the, the biogas production. Like sulfide, okay? The ratio between COD and sulfide should be lower than 10. Salinity, 50% activity, inhibitory, concentrations about 25 gram sodium per liter. And then the last one is that we need very low long chain fatty acids. All right. So now the drawback of anaerobic MBR. That means we have problem with, because the first stage that the VFA, the volatile fatty acid accumulation, then is that they will make the problem because the pH value will changes and create the problem for the whole system. Methanogenic inhibition, we just say about the ammonia, just say about the sulfide, we just say about the long chain, the fatty acids or something like that. Then we just think about this is the problem. So why we have an up and down too much per day? It's not really stable, just because of that. And unstable, process, and serial membrane fouling. As you know, this is a very headache one for the membrane fouling, and then low nutrient removal efficiency. So that we have a 1, 2, 3, 4, 5. That's the 5 major drawbacks of anaerobic MBR. Okay, so the membrane fouling, I just very quick to go through because of the time constraint. But anyway, is that the membrane fouling really more serious. Like the reason why the people don't like to use the anaerobic MBR. Quite serious. Okay, because when the fouling, then the treatment slot will drop, and then the system downtime is higher, and then we have to clean the membrane with the chemical or physical cleaning, and we have to increase the gas scouring and sludge recirculation, and then the membrane become, to get that the shorter time, so the lifetime is short, and then of course we have to pay the money for that, so that is not good. The fouling mechanism, I show you here for this figure. You can see we have a K formula. We have a pore constriction and termediate blocking or complete blocking. And that kind of thing you just see is that because inside the wastewater we have a sludge flux, we have colors, we have a solutes. All right. So this for the pore constriction is very easy to see because that is the, like the smaller than the pore size, they come inside and they create the blocking problem. And the K formation, we have to think about is that whenever they drop to on each other. So that means firstly it's all right, but after some time they become the cake. They become the layer and they block the thing, and they left very difficult for the water to flow through. Okay, and intermediate is similar because the blocking from the beginning, the particle to come arriving on the already, like the acids on the membrane or something like that, and then just because of that later state is a cake formation. And complete blocking easy because the size is too big. So that means outside they block the fully block the pore. Okay, fully block the pore. Outside, it's not inside. This is the inside. All right. And then we have the colloidal fouling, we have organic fouling, we have a biofouling, inorganic fouling. But I just want to say about biofouling because for an anaerobic MBR, the more serious reason is the biofouling, because the microorganism they grow on the on the water surface and even inside the pore. That is a problem. And when they grow like that, they just react that the like the fouling, and then that kind of fouling is very headache. Because we cannot use the physical, like the technology to treat that. We have to combine physical and chemical and something to treat the biofouling. And then when this one is that, I just very short to explain to you is that if we want to control the fouling, we have to go from the membrane characteristics, that means membrane properties, okay, like the roughness, like the surface charge, this kind of thing, or pore size. And then the membrane operation, the condition, for example, flush, wastewater, relaxation, cleaning, or something. And then we have to consider the bioreactor operation. This one is that like the HRT, HRT, or temperature, or pH value, or this kind of thing. All right, and the substrate terms, for example, like you just see about the particulate COD, for example. This is the thing. But main thing, if you learn about the membrane fouling, we always tell about the SMP. That means soluble microbial products or the EPS. So that means the extracellular polymetric substances. Okay, so this is that kind of, that is the slide here. You can see this is the way we think to control the fouling. And then the fouling management, yes, as I discussed with you already. But membrane cleaning, we need to know the proper way to clean the membrane. And then is that normally we talk about the physical cleaning and chemical cleaning. And physical cleaning and the what is that, the chemical cleaning strategy is here. For this slide, I just show you when we have inorganic fouling, for example, we can go for chemical cleaning. For example, particulate or colloidal, I mean like the fouling, then we use chemical cleaning, and then we can use the backwash, okay, cleaning or something, then no problem. But come to the biological biofouling, sorry, I just say biofouling, then we have that cleaning, we have chlorination, and then we have the acidification, and then chemical cleaning. All right, so on this kind of thing, we have to treat, we have to show the biofouling. Not easy, not easy. Organic, easy. Organic, we just use the chlorination or chemical cleaning. It should be okay. Then we go to the develop hydraulic anaerobic MBR. Why we have to have a hybrid? As you know, is that hybrids, that means we have combined different units together, and then to make it that the higher removal efficiency, or I mean that the performance, higher performance. And then here, the anaerobic MBR, the weakness is the removal efficiency. So that's the reason you can see we need to have the pre-treatment, and then we have a post-treatment as well for anaerobic MBR. And then to enhance the process stability, to enhance the effluent quality, to improve the bioenergy production and treatment capacity. All right, and the case study, I just show very quick, just go through that. The case study, we have the anaerobic MBR and the anaerobic fluid, the bioreactor or something like that, to use in the slaughter, I mean like the house waste treatment. And then they can do the good job, for example, overcome VFA accumulation. And then two-stage anaerobic MBR to treat the cheeseway. Then we can have excellent treatment performance for the high loading wastewater, for example. And then we use the AFPR with that with the anaerobic MBR. We just say is that because this kind of thing, when we use for the domestic wastewater, we think is that whether it's worth it to do it, okay? And then when they combine the two, I mean like the two system, and if we don't have energy cost reduction, and if we don't have efficient methane production, forget it. We are not going to pay the money for two units to combine together. And the hydrogen delivery unit with the anaerobic MBR, we say is a municipal final effluent, reduce nitrate below the detectable level. That's just only the nitrate. They focus on the nitrate. So this kind of thing, I just show you through that. We have the upflow aerobic slug blanket USB, and then together we can have the biogas. It's good biogas production, and I think is that really attractive one with the 0.42 cubic meter methane per cubic meter day. All right, and then we use the expanded granular sludge bed. And then we use together with the membrane, then we have a pretty go up to 0.58 cubic meter methane per day, per cubic wastewater per day as well. And for the anaerobic fluoride bed reactor with the membrane unit, then we just have that the 4.11 mole methane per cubic meter. And then the last one I just want to, introduce is that the anaerobic dynamic membrane bioreactors. And this one, even though we can see it's not really, go to very high like the methane production, but the good thing is that about the membrane, because the diamond membrane, you just say the diameter, so that means we only need to have some base, and then the solids is that to build up there, and then they become the membrane. but we need not to use like ultrafiltration or microfiltration or something like that. No, we don't need to. Okay, and then another anaerobic membrane distillation. This is the latest technologies about the MD. Okay, and then we use that under the anaerobic condition, so then we can have that, and also anaerobic osmotic membrane bioreactors. So when we talk like that, the osmotic one maybe. Actually, we cannot say maybe, we have to say should be, the forward osmosis, okay? Because the reverse osmosis, normally we use as the post treatment. We never use in that, the pre-treatment or something with the bioreactor. Okay, so now we go to the sustainability analysis and future perspective. What is that? What is sustainability analysis? That the reason is that when we talk, we need to have some analysis to go to the conclusions. Otherwise, very hard to say is anaerobic is the future sustainable wastewater treatment technology. No, we can't. So this is that through my, introduction and discussion about, we just see, we know the waste minimization significant from the anaerobic MBR because sludge production is very, very low. Renewable energy production, yes, because only anaerobic MBR have. So renewable energy production, yes, the answer 100%. Reduce footprint, yes, again, because for example, we don't need to have days and days for the HRT, and then excellent effluent quality. This kind of thing is when we say yes, we a little bit second because it's true. That one is that it depends on how you think. Excellent effluent quality when we use up the hybrid system. An anaerobic MBR hybrid system. This kind of answer is 100%. Yes, excellent effluent quality. So anyway, when we satisfy for in terms of that, we can say, yeah, this anaerobic MBR is quite sustainable. All right, and now it's very interesting. We want to make the comparison from the different indicators. For example, from the organic removal to the biorecovery to mode of treatment, footprint, biomass retention, nutrient requirement, or whatever in there to make the comparison. And then you can see that is interesting here. Anaerobic treatment and anaerobic treatment, anaerobic MBR and anaerobic MBR. Okay, so now what we do is that we count on the red color, whatever I just made. So that means anaerobic treatment, they have a 2 top. So that means 2 good things. And anaerobic treatment have a 1, 2, 3, 4, 5. Yes, they have a 5. Anaerobic MBR have a 1, 2, 3, 4, 5, 6. And then for the anaerobic MBR, have a 1, 2, 3, 4, 5, 6, 7. So when we make that kind of comparison, we are very happy to think about an anaerobic MBR. All right, just think about an anaerobic MBR. And then we are smart enough to use the anaerobic bioreactor or some of the other bioreactor to support an anaerobic MBR as the pre-treatment or post-treatment. All right, the future perspective. That is my suggestion about it. When we talk about the future perspective, we have to think how to apply the anaerobic MBR in a very, the reasonable way. So get that the people, accept for in the whole world. It's not only 1 or 2 countries or something. Only thing we can do is that life cycle assessment. Because in the future, definitely we have to do a lot of research about the anaerobic MBR using life cycle, assessment. Or we have to think about circular bioeconomy. Because that's the only thing you can say to the people yet in Arabic. They already satisfied for this kind of thing and that kind of analysis or something like that. And then the second thing is an Arabic fouling control. In fact, is that at the moment, we do not have a lot about the membrane fouling in an Arabic MBR. It's not like Arabic MBR. We have a lot of research on that, and we have a quite, almost saturation about that. But it's that about an Arabic fouling control or an Arabic membrane fouling, we need to do much more. So that is the future work we need to do. Okay. So number 3, multi-stage hybrid and Arabic MBR system. That is, we need to be smart enough to combine with the other to make an Arabic MBR become perfect or become, the sustainable system. All right. So this is a lot of research we have to go, because we cannot just say is that, whatever we check another, we put in together as a hybrid. No way, because we need that the what we say appropriate, or something with the optimal one or something. So this is that think about it. System control to achieve optimal biogas recovery. This one is another thing we have to work on, especially for the operating condition. Operation, this is a bioreactor operating condition. Or we have to think about enzyme, how we make more, have the different kind of enzyme to support for the pathway, for 4 different pathways to increase the biogas production. And the last one is really interesting. Research on microbial community structure and its influence. In fact, if we just only say removal, very simple, because an Arabic breakdown the organic, we know, everyone know about it. Okay, very clearly. But come to the microbial community. That is the thing we can do some research about the community, and which kind of community is really a main thing to support, especially for biogas production. A lot of work, a lot of research we can do about it. And this is a little bit more microbiology, but we need to. Okay, so this is another good for the future perspective on the anaerobic MBR development. Okay, so now about the conclusion. The conclusion is very straightforward. Anaerobic MBR, potential for various types of wastewater, as I showed to you, industry wastewater, municipal wastewater, domestic wastewater, whatever they can use. And then this is quite sustainable technology. At the moment, we can think about it, but we have to do a lot of work to prove, to convince the people. All right. Biogas recovery, reduce the greenhouse gas emission and provide energy. That is the fact. Because when we have the biogas recovery, of course, that's we reduce the greenhouse gas emission and provide the energy, because we try to collect the biogas and we yield for the, the bioenergy. Okay. Complex digestion is influenced by many factors. And then, in fact, is that mostly we just need to play around with 4 key factors. One is the pH, second is temperature, third is HRT, and the last one is HRT. And then the last one is seemed to be the most important one, because we cannot only work in the lab with the lab scale. How good it is not going to help. if we really to make the practical application, we need to study at the large or even go to that commercial scale. So that means go up to full scale, pilot scale. Because from that scale, we have to go to the pilot scale. From pilot scale, we go to full scale. And then that only that we can apply the technology. Okay. So when we have with the large scale, so then we need to talk to the people with the large scale about the biogas recovery, process control, process efficiency, membrane cost, and folding. That is the key matters we need to show to the people. Okay, so I think that because the time, I need to control the time, and it seems to be it's all right at the moment. So thank you very much for your attention, and have a happy day. And if you have any question, please just raise, and I try my best to answer your question. Okay.
Okay. Thank you, Hong. So, Satria, please.
Okay, so we already have a few questions. Let me share the slides with you because we already write it in slides. Pardon me, I'm going to share my screen.
Hello. Yeah.
So we already have question whether from YouTube or from Zoom. This is the first question from YouTube, from Rani from Research Unit of Technology in Limbah, Indonesia. I'm wondering whether there's an optimum COD concentration or load to achieve high COD removal, or is it more to do with wastewater properties? For instance, if there's a recalcitrant compound in the wastewater, will they accumulate in the bioreactor instead it goes with the effluent? Maybe you can answer the first question, sir.
Yeah. So one by one, I will.
Yeah. So yeah, one by one.
One by one, right?
Yeah.
The first one is that whether there's an optimum COD concentration or not to achieve a high COD removal. I can answer that question to you is that at the moment, it seems to be for the organic loading rate, is not about 10-fold higher than the Anaerobic MBR or the bioreactors. So we don't worry much about the concentration of the organic. And then the higher organic, it seems to be the better removal efficiency. That means the COD removal efficiency. So when it's less, for example, like the municipal wastewater treatment, when we use an Anaerobic MBR, we have to think of condense the COD concentration. So that's the reason we use the forward OMC, because the higher COD concentration is better for an Anaerobic MBR. So that is my answer, because that we do not have exactly the optimum COD concentration, or the organic loading rate, but we know is that higher, the better, and even much about 5 to 10 times, organic loading rate for the anaerobic MBR. Okay, so even the organic shock, which when shock comes to suddenly it's very high, anaerobic MBR still very okay. All right. So now I just say, for instance, for instance, if there, like recalcitrant compounds in the wastewater, would they accumulate in the bioreactor instead of goes with the effluent? For this one, it seems to be some. I can say is that definitely have a some will accumulate in the bioreactor. But if you see, the only thing how they accumulate, right? If they accumulate in the sludge, for example, and then we withdraw every day, or we recirculate, and then some part we waste, in some way, it's still all right. And then sludge will go for the treatment, then all right. But I tell you, it's not the big the matter at the moment, because this is very, I can see it, the amount is so small. Okay, but I can tell you, yes, some they accumulate. All right. And then the Dr. Ian, okay, I just want to tell you about that. Cost and benefit analysis in Anaerobic MBR. Okay. When you want me to tell cost and benefit analysis of MBR, it just only you just ask me about the economy, bioeconomy, or you want to do something about the cost and benefit analysis and Anaerobic MBR. I'd like you to tell me more about that. If about the economy, yes, some research already have already done, and then they based on that, based on the capital costs, operating costs, and the saving, the energy, like saving or something very positive for an Anaerobic MBR compared to aerobic MBR. So that is about the bioeconomy, or we say circular bioeconomy is a pretty positive for an aerobic MBR. Okay. And then if possible, treatment antibiotic from hospital, from wastewater. Yes, my answer is 100%. My answer is, indeed, we can treat the antibiotic from hospital wastewater. No problem at all. Because we did a lot with that swine wastewater in very high concentration of the antibiotic. And then the removal efficiency is quite very, very high compared to the other, bioreactors. All right. So this is that very, I'm very confident about the anaerobic can do that to remove the antibiotic from hospital wastewater. Okay. So now to the Awalina, right? Have any suggestion due to how to separate ammonia generation during the process? Do this process also have any relation with the biofouling on the membrane module? Okay. Any suggestion due to how to separate the ammonia generation during the process? That is the thing. Because as you know is that nitrification, denitrification, we need nitrification to convert the ammonia to become the nitrate, and then from denitrification or something like that. For the anaerobic MBR, we do not have the aerobic stage. So in this situation, if we use only the anaerobic MBR without any oxygen present, of course, in this situation, the ammonia maybe is a problem because they may have to accumulate and then to affect the the efficiency. Okay, but in somehow the ammonia we can combine. So that's why the anaerobic MBR need the hybrid system just because of that. Or we think about we can use animals. Okay, we can use animals to apply for an anaerobic MBR, for example. And then is that this process, I think is that in my opinion, the biofouling from that is not significant, or even it's not really, because for the biofouling, just remember the polysaccharide and protein, that too is really create the problem with the with the biofouling. So from the polysaccharide and protein, the ratio, and then we see the SMP, EPS, then we just try to control the membrane folding. But it's a very rare to, just because of ammonia, generation or something, and affect the biofouling. Okay, but yes, for the organic fouling, yes, in somehow, yes. Okay, and okay, so any more questions?
Yeah, so we will move on to the second batch of questions. There is 2 more questions from YouTube.
Yeah.
Yeah, please answer it, sir.
For the MBR remove color, okay, so that is at the moment very rare or very few research to work on the MBR. I mean, like the removal color by MBR. I think that is the, I don't know exactly what that, whether the MBR can do efficiently remove the color from the water or the wastewater. But it's one thing you need to play around for that, because when we talk about the color, right? And then it's that if I just say, if I were you, I will use the biochar to add inside the MBR reactor. So that means I can use the biochar or activated carbon or something like that to, I mean, to add into the MBR. And that kind of MBR, either aerobic MBR or anaerobic MBR, will work well to remove the color from wastewater or from water. Okay, so this is the thing I suggested, that in somehow that okay to remove the color, because that is the thing. And then because of the membrane, as you see, is that we have the color is that for the true color, yes, true color and apparent color is something is that about the solid, the size of the solid in there. For the true colors, normally because of the color that means colloidal matter in some way is that, or the soluble, yeah, mainly the soluble, I mean like the solids. So then with the membrane, and then with you use, for example, the other way can use is that you can use nanofiltration, for example, then the color will be removed well. About the narrative that how to control temperature in an anaerobic MBR or full scale. For that one, definitely is that they use is the only thing they use is that like the normal temperature controller. That is very costly. In fact, when we want to increase that the temperature from, for example, from the mesophilic 35 degree, 35 centigrade to 55 centigrade for the thermophilic, we have to pay a lot of money. So that is nothing special for that. Only the temperature controller, whatever they do, then that is really, really costly. And I tell you, nothing special at the moment for an anaerobic MBR, or I mean, like exactly the same. They control like the lab scale, they control like the pilot scale or something, exactly the same. Nothing special. I can tell you about it. And the FE, what do you suggest to be controlled? What is that? You suggest to be controlled in an anaerobic system? It's the temperature, the pH, or maybe the loading rate. Remember, I haven't that. To control the anaerobic MBR system, just for main parameter, I show in the slide already for you. pH, temperature, HRT, and SRT. All right, just remember about the loading rate, about the organic loading rate. I mentioned the higher the better. So it's all right for that for the loading rate, but for the temperature, pH, HRT, and SRT is really, really important. Really, really important. So that means we need to play around with these 4 parameters. Okay. Sophia, can it be used on treatment of the mining waste? You mean CN?
Cyanide. That one is
okay. Cyanide. Okay. My answer is yes. My answer is yes. I mean, like the confident, yes. No problem at all. Okay, no problem at all. Yes, it's all right. It's all right. But I just say it. But I say to you, need to have some pre-treatment. Need some pre-treatment, or you integrated system. That meaning that in anaerobic you add something in to enhance that the removal efficiency. At the same time, you have to reduce the inhibitor in that for the methanol bacterial, or I mean some the other sensitive with that the toxic substance or something like that. All right.
Okay, we still have 2 more questions. Prof, maybe we still have 8 minutes, so I assume that you can ask.
Okay, two more.
Yeah,
Wait.
the last 2 questions.
Yeah. Okay. Recently, wastewater treatment by using advanced oxidation process (AOP) become more considered method in organic wastewater treatment. Yes, method of ozone, UV, or non-thermoplasma is a set of the AOP. Yes. What do you think about combination of MBR method and OOP? Do you think the combination could increase? 100%. Perfect. If you really can use that the AOP together with the MBR, either Arabic MBR or an Arabic MBR is excellent. Really, is that in somehow, especially, I think I can expect the removal efficiency, especially from the organic, from COD, it should be 100%. And also the biogas, I mean like the, what is that? The biogas productions on what go to the top one. I think it's maybe even I just see about, for the, it's go up to the, just that, not only 2 point something, I think only 5 kilowatt per cubic meter COD, I think like that, because really high. But the only thing when you do that, yes, it's applicable and feasible as well, but the economy, you need to do the LCA, and then you need to do the economy to convince the people about the cost, because that 2 kind of thing to put together, whether the costs go up higher than the other, I mean like the system. Okay. Novita, is there a possibility that micropollutant from wastewater to be carried over to gas? If yes, how to anticipate it and how to capture dissolved methane in wastewater? This is that. Is the thing is that is there a possibility that micropollutants from wastewater to be carried out over to gas? The micropollutant is, because the reason is the quantity, I just seem to be the quantity. They can convert to gas, yes, but it's not much. So this is because the quantity, just only because the quantity, but just the organic. Yes, so if we do pretty well, whatever the organic, even is not, I mean like the something, but I have to tell you that biodegradable, but cannot be non-biodegradable. So biodegradable, even that's more micropollutant, yes, they can carry over to gas, no problem. And how to anticipate it is nothing special, but that I say to you is that if you want to carry over to gas, then you have to control well for the hydrology, especially hydrology from the beginning, okay? And then go to the second stage of the fermentation. In that 2 stage with the enzyme, 2 kind of the enzyme and 2 kind with that the bacterial, then you'll be successful to convert the micropollutant to the biogas. All right. How to capture dissolved methane in wastewater? This is very, very tough work, in fact. So let the researcher think about it. And then is that, just think about the nitrous oxide. Just think about the nitrous oxide, for example. Nitrous oxide in the wastewater together with methane and what is their chemical reaction or biochemical reaction to make them to release the nitrogen and carbon dioxide. So in this situation, we do not have problem with the methane dissolve, and at the same time we can show the nitrous oxide. This is another, I mean, like the greenhouse gas, okay, greenhouse gas, so a nitrous oxide, and then the methane one. So this is just only, I just say for example. So that is the way to think, and then think about the pressure, for example. The pressure, and then think about in some we just say some attractive or acceptor. Instead of when they dissolve to the water, we need to add something to attract or accept the carbon, the methane. And I say to you, the methane can be something with the nitrogen oxide, for example. That is the way, okay? That is the way to capture the dissolved methane in wastewater. But in fact, now with my idea, I like to make the methane completely release to the bioreactor, and then we can collect fully instead of we use some the other to reduce the dissolved methane, to avoid the global warming problem. Okay, yeah. So yeah, so I think another 1 or 2 minutes. So if anyone, I don't know whether I have time to answer more questions, but anyway.
Yeah, I don't think it's the last question, Sean, because we don't have much time left. Maybe we would like, before we end the session with your closing statement, maybe Professor Chandra, as your colleagues, can maybe want to add like something.
Yeah.
Okay. Thank you very much for very nice lecture. And in this room is around 30 in the Zoom room, but I think in the YouTube is more than 100 something participants watching your lecture. I think it's quite interesting, and some of a number of participants asking, you may share your presentation, or if it's possible.
I can send to you. No problem.
Yes, I think a number of participants asking about the.
I send to you. No problem. No problem.
Okay. I will share to the participant either in the Zoom room or in the YouTube.
Yeah, no problem. No problem. No problem.
Okay, yeah. Thank you very much, Hao. So it is very nice, and then to having you here, and we'll meet again maybe in Sydney or in Bandung or in Bali.
We'll meet again. Hopefully very soon.
Very soon, yeah.
Maybe early next year, I think.
Early next year. So Satria, so we will have a photo session, or?
Yeah, we will end the session by having a photo session with the participant in the Zoom room. And the participant in the Zoom room can turn on their cameras and then close together with also Professor Moon. Okay. We will wait first for the participants to turn on their cameras, and then I will take the photos by counting down from 3. Okay. And just waiting. Okay, I guess a lot of people has already turned their cameras on, and I will take the photos by counting down from 3. Please give me your warm smile. Also to Professor. Okay. I will start the documentation session. 3, 2, 1. Okay, once more. 3, 2, and 1. Okay. Thank you, Professor. Many thanks to you. Maybe you would like to.
Thank you. Thank you.
I will send the file to you.
Yes.
Yeah.
Okay. Thank you very much. Thank you.
Many thanks to Professor.
Okay. See you all. Okay. Have a happy day.
Everything.
Thank you very much.
Okay, so karena teman-teman sudah keluar dari ruangan, maka saya juga mengucapkan terima kasih banyak kepada seluruh peserta dari YouTube. Di sini kami akan mengakhiri live streamnya dan semoga kami dapat berjumpa lagi dengan peserta-peserta di YouTube pada webinar-webinar PSLH lainnya. Saya mohon izin untuk mengakhiri webinar ini. Terima kasih. Assalamualaikum warahmatullahi wabarakatuh.